Okay, we are on gamma right now. Gamma distribution. Gamma distribution has a lot of application in insurance. Okay, if an insurance company want to know the total claim, not just one claim, total claims within a particular interval, they're actually going to make use of gamma distribution. Okay, what about the total amount of rainfall? Okay, the aggregate, the accumulation, of course, they're going to make use of a gamma distribution. So when S follow gamma, with parameter alpha beta, okay, f of s equal x raised to power alpha minus 1 exponential raised to power this divided by gamma alpha, beta raised to power alpha, this greater than 0, and this greater than 0. Now I'm going to establish a connection now between the gamma distribution and the exponential. Do you know that gamma 1 beta, gamma 1 beta, okay, gamma 1 beta is the same thing as exponential beta. Okay, plug in wherever you see alpha here, plug in 1. When you plug in 1 here, right? When you plug in 1, you're actually going to have this. If you plug in 1 wherever you see alpha, okay, when alpha equal to 1, okay, if alpha equal to 1, okay, alpha equal to 1, that very 1 means a single event. How long are you going to wait for one event to occur? But when alpha is more than 1, you are talking about more than one event. That will be for gamma. Okay, now when you have gamma, now the next thing I'm actually going to do now is, how do I actually, the expected value of S is alpha beta. The variance of S is alpha beta squared. Oh my God. When I plug in alpha to be 1 here, that will become the mean of exponential. When I plug alpha equal to 1, that becomes the variance of exponential. Do you see the connection? Okay, now what I want to do now, I want to generate a moment generating function, you know, deriving moment, deriving mean and variance and the like, when you make use of moment generating function. That would be super cool. Okay, so expectation of ETX equal integral 0 to infinity e raised to power ts f of s dx. Okay, so right now 0 to infinity e raised to power ts s raised to power this over that divided by gamma alpha beta raised to power alpha ds. I just plug in the gamma distribution now. Okay, so right now I'm actually going to bring the constant out. Okay, when I bring the constant out, I'm going to have ETX minus x over beta this ds. Any question? That's algebra, right? Okay, before you start doing calculus, like I used to tell researchers around me, majority of what we do in math is algebra. Even there's algebra in calculus. Before I'm going to integrate, I'm actually need to first tidy it up. Okay, you get what I mean? Okay, now so now I need to, so mx of t equal 1 over gamma alpha beta raised to power alpha 0 to infinity exponential. Okay, I can write minus x. Okay, so if I write minus x, so this is going to be 1 over beta. Okay, then minus t. Okay, x raised to power that dx. Any question on that, on what I just did? I actually want a negative on the exponential. Okay, mathematically. Now, if you take a look at this now, if you take a look at this guy, okay, I want to see if I can apply a gamma function here. But that would be difficult to apply now, because if I want to apply a gamma function, everything here has to be what is here. and what is here. So all of us use a substitution method. Let y be whatever, let y be this. Okay, let y be that. Okay, this is the same thing as if you try to simplify. Okay, x, right? If you simplify, what is x? Okay, x equal beta y. Okay, x equal beta y over 1 minus bt. Okay, if x equal to that, okay, what is the y ds? The y ds, okay, the y ds is going to be this. Okay, what does this imply? That implies ds equal beta dy over 1 minus bt. Okay, if that happened, I'm going to start plugging in now. Okay, like I said, if there's any one of you who has lost touch with calculus, visit with me during my office hour. My office hour is conducted remotely. I'm going to walk you through basic calculus that you need. Now, if I want to write this right now, ms of t equal 1 over gamma alpha this, okay, 0 to infinity. Okay, this is going to be exponential raised to the power y, and x. What is x? X is this, beta y over 1 minus beta t raised to power alpha minus 1. What is ds? Ds is beta dy over 1 minus beta t. What have I done? I've eliminated x. Okay, now I just need to simplify right now. Okay, this guy. Okay, beta. Here you're going to have this. Any question? That's algebra, right? Okay, let's simplify now, right? Okay, so look at this guy. That will be beta raised to power alpha. It's going to cancel that guy, right? Okay, take a look at this guy. Okay, when you take a look at something is missing. Let me see again. Okay, what is missing is the y. Okay, so let's take a look. Yeah, that's what is missing. Okay, so now 1 over gamma alpha, 0 to infinity, this, then divided by 1 over beta t raised to power alpha. Now take a look at this guy. Can somebody tell me this? What is that? What is this? Based on what we've done today. That's a gamma alpha. Is this not gamma alpha? That's a gamma alpha, right? This is an integral definition of a gamma alpha. You remember the other time I talked about gamma function, right? Okay, don't forget. Okay, recall. Okay, recall from gamma function. Okay, gamma alpha is what? Is this? Okay, whether in terms of x or that, dx. Okay, take a look at this. Y. That's a gamma alpha. Okay, so what I'm going to have right now, okay, mx of t equal, okay, that's going to be gamma alpha divided by gamma alpha, then 1 minus bt raised to power alpha. This cancels that guy. So what do we have? That is the moment generating function of a gamma distribution. Do you know that when alpha equal to 1, what happened? When alpha equal to 1 here, it becomes a moment generating function of exponential. Look at that. Okay, so when you have this guy now, you can derive the mean. Okay, I'm not going to, let me see, let me look at the time. Okay, so because of my time, I'm just going to say, when you differentiate this guy, where you set your t to 0, that will give you this. Okay? When you differentiate that, again, when you set your t to 0, okay, you're actually going to have something else. You can see that. But what I know, the variance of x is expected value of x squared minus expected value of x all squared. Okay, so which is m prime prime, okay, x of t, okay, where t equal to 0 minus m prime s of t, where t equal to 0 all squared. We eventually give you this guy. You can try that. Okay, so what have I done? Okay, with that you'll be able to derive, the moment you have your moment generating function in place, you'll be able to get, whatever, characteristics of interest you want to get. Now, if you take a look at what I'm showing you now, there's a lot of flexibility in gamma. Okay, the shape of the gamma depends on the values of the two parameters indeed. You take a look at what I'm seeing now. When alpha equal to 1 and beta equal to 1, you see that shape. When alpha equal to 2, beta equal to 1. So it depends, the shape that is going to come out actually depends, on the values of the alpha and the beta. So what I've been able to do now, take a look at this guy. Okay, the mean is going to be alpha beta. The moment you get your moment generating function correctly derived, every other thing is going to be cool. Okay, as far as that is concerned. So gamma distribution is very, very useful in survival analysis. Okay, very useful in survival analysis. At times the doctor may want to know how long they're going to wait before a patient recover from a particular illness. Okay, following intervention. So there's a lot of application for that. Look at this example 6.27. A biomedical study determines that the survival time in weeks as a gamma distribution with alpha equal to 3 and beta equal to 4 for a certain dose of a toxicant. What is the probability that your rat survive no longer 10 weeks? Okay? So the variable of interest x will represent time in this scenario. Does that make sense? Okay, before I go into